Hello, welcome back. Here is just a short little, I only have 4 slides for this little mini lesson, just to talk about the different types of acids, review the vocabulary that goes along with acid-base chemistry, and give some examples of the different types of acids that we see in our bodies. Okay, so on this slide, usually what I do when I'm teaching this in lecture is that I want to make sure that we're semi-comfortable with all the terminology that goes along with acid-base balance, because I know sometimes it can get confusing when we're talking about hydrogens going up, pH is going down, acids, bases, all this kind of stuff. So I wanted to make sure that we have kind of a steady footing on this. If you are unsure about any of the concepts of acid-base chemistry, stop by a Zoom office hour, send me emails, get some clarification, because you need to really understand how all of these things work together to be able to then apply it to your article assignment, the ABG article that you'll be working on for this week's the systems case study, because it can be a little bit confusing. So let's just go ahead and dive in with these terms, and we'll talk about some different types of acids that we'll be seeing in this chapter. So first of all, pH is a measurement of hydrogen ion concentration. You don't need to know the mathematical calculations or how it's figured, but just know that when we talk about pH, it is the concentration of hydrogen ion. So the relationship of that is, so hydrogen ion concentration, these little brackets around the H plus mean the concentration of, it's like chemistry shorthand. If this goes up, if you have an increase in hydrogen ion concentration, what that means is the pH number is going to go down. So remember, it is a pH scale from 0 to 7. Sorry, from 0 to 14. 7 is neutral. Anything less than 7 is going to be an acid. Anything greater than 7 is going to be a base. So when we talk about the pH number, when you have a higher concentration of hydrogen ions, that is going to result in a lower pH number, okay? So that is our measurement of pH. So then the next couple terms, neutral, acidic, and alkaline, again, that's referring to that pH scale. So I don't have a lot of room, so I'm going to do a vertical pH scale here. So if this is 0, sorry, that's not going to be 0. If this is 7, this is 0, and this is 14. Anything in this range is going to be an acid. Anything in this range is going to be a base. And 7 is neutral. Okay, so what that means is if we have a high hydrogen ion concentration, we are going to be down in 0 to 6.9, if you will. If we have a low hydrogen ion concentration, we're going to be 7.1 or above, up to 14. So that is how our hydrogen ion concentration relates to our pH value. Okay, so then when we take a look at an acid or a base, what are those things? Well, they are things that are going to affect that hydrogen ion concentration in solution. So if you have a substance that when mixed with water, when it dissociates, which means it breaks apart, if it breaks apart and increases the concentration of hydrogen ions, we call that an acid. So like hydrochloric acid, HCl. When that gets mixed with water, right, what happens is the hydrogen ions break apart, the chlorine ions break apart, and now you've just increased your concentration of hydrogen ions. So it is an acid because the HCl breaks apart into hydrogen ions, increasing the number of hydrogen ions in solution. If we had a base, so sodium hydroxide is a pretty common base. If we mix that with water, what will happen is the sodium will break apart. Sodium is just sodium. It has nothing to do with pH. But now what we have is this OH minus, it's called the hydroxide ion. Now, if it's mixing with water, water just kind of floats around. Sometimes the hydrogens come off. So it will steal any hydrogens and convert that to water. And so basically what we're doing, the OH minus is taking hydrogen ions out of solution. It is a proton or hydrogen ion acceptor. So sodium hydroxide is considered a base because it reduces the concentration of hydrogen ions in that solution. So this definition, a substance that dissociates to release hydroxide ions or to tie up hydrogen ions, increasing the pH number. Okay, so that's our idea of what an acid and a base is. So an acid is anything that can increase the concentration of hydrogen ions, making the pH lower, while a base is anything that is going to decrease the concentration of hydrogen ions, making the pH higher. Okay, so then we take a look at a salt. So a salt is usually a positively charged ion bound ionically with a negatively charged ion. So the positive sodium is attracted to the negative chlorine, and that is a salt. When they mix with water, they dissociate. You get your positive cation and your negative anion. We will also see something like this. This is called sodium bicarbonate. Here's your positively charged sodium and your negatively charged bicarbonate. We saw the bicarb ion in our carbonic acid bicarbonate buffer equation, which we'll see again here shortly, and that would be considered a salt. Okay? Or you might have magnesium chloride. Magnesium chloride or calcium chloride. I might not have my numbers right. I might think it might be CaCl2 or something. I think that might be right. So anything that has a positively charged ion attracted to a negatively charged ion held together by an ionic bond, and when they dissociate, they become electrolytes, those charged ions. Those are considered salts. All right, so then the last word here in our little vocabulary list is a buffer. So a buffer is something, usually a molecule, something that has the ability to maintain pH even when you add acids or bases to it. So it helps to maintain homeostatic levels. So usually you're going to see buffers that have the ability to either release hydrogen ions if they're needed, or they can tie up hydrogen ions as needed. So we'll be doing a little talk on buffers here in another mini lesson. So buffers help to maintain your normal pH. And so for our blood, our normal pH is between 7.35 and 7.45. All right, so again, if you are unsure about how to understand any of these things, your confidence level with any of these terms, your ability to go between pH and acid and base and hydrogen ions and hydroxide ions, if that's still a struggle for you, get some help. Let me help you clarify. Okay, so there's going to be some acids that we're going to be seeing, biologically produced acids. There's one big one that we're really going to focus on the most, which is going to be carbon dioxide or carbonic acid. But let's talk about some of these other ones. So we have what are called fixed acids, where fixed acids stay in solution. They don't have the ability to be volatile, which we'll see is another category. So they do not, they can't be dissolved or change their nature like we can see carbon dioxide does in a little bit. So for example, sulfuric acid or phosphoric acid, if we have high levels of those, typically they're going to be excreted by the kidneys. And then that's how our body really deals with them. We don't produce them a lot if we metabolize amino acids, which isn't a large portion of our energy production. We usually break down fats and carbs. But if we were to break down proteins and amino acids, we might produce some of these phosphoric and sulfuric acids. So those are what we call fixed acids. Organic acids are things like the intermediates of metabolic pathways, like pyruvic acid, lactic acid, keto acids. These types of things are normally produced, but they typically don't stick around for a very long time. So lactic acid is broken down. Remember, by the Cori cycle, we saw that way back in 231 with muscle physiology. Pyruvic acid is sent directly into the Krebs cycle, as acetyl-CoA, so it doesn't stick around for a very long time. So we do have the ability to produce these in a normal, healthy individual. They're usually metabolized and changed into non-acidic forms relatively quickly. However, if you are dealing with a physiological problem like a ketoacidosis or a lactic acidosis, something's wrong that is allowing your body to build up higher quantities of these organic acids, which could impact your blood's pH. And then the last category of acids is called a volatile acid. So this would be the main one we're going to talk about is carbon dioxide. And the reason why is because it can shift from the gaseous form of CO2 into the dissolved form of carbonic acid, which quickly dissociates into the bicarbonate ion and the hydrogen ion. So that's the acid part, right? So this is the acid part of carbon dioxide. CO2 itself isn't an acid, but when it mixes with water, it produces a carbonic acid, which dissociates and produces those hydrogen ions. So that's the definition of an acid. So this volatile acid was really key into our regulating our blood pH. And then lastly, since that's kind of what we just ended on, this is the kind of the teeter-totter idea that we saw back in your guys' case study when you have this relationship between carbon dioxide and pH. When you're in homeostasis, that bicarbonic acid bicarbonate buffer equation is at equilibrium. The teeter-totter is balanced. You have the same amount of reactants and products and going back and forth. If you were to increase your carbon dioxide, what that does is it drives the equation to the right, producing more hydrogen, which is going to make the pH go down. So they are in inverse relationship. CO2 goes up, pH goes down. On the reverse of that, if PCO2 decreases, right, we are going to be driving the equation in the opposite direction. I don't like that they actually drew it in the opposite way because the arrow is still going in the same direction. But if you'll take a look, we're going to be producing more hydrogen ions. And to do that, the hydrogen, the free floating hydrogen, is going to be bound up by the bicarb to produce carbonic acid, which then breaks apart into carbon dioxide and water to replenish that lost CO2. And when we tie up those hydrogen ions, right, we reduce hydrogen ions, we're going to increase pH. All right, so that's that relationship between CO2 and blood pH. You kind of answered some of those questions in that grandpa pulmonary fibrosis case study a couple body systems ago. All right, so that's our little mini lesson on acids. Now we're going to have another little mini lesson on buffers. What are the ways that our body can maintain a proper pH between 7.35 and 7.45 with some various mechanisms? And you can bet that this equation is coming back. All right, I will see you next time.